Let's look at quantum numbers, please. Use ML, MS. Look up, please. Let's look at what is it called? Quantum numbers. Leave out definitions to your text and your notes. I want to focus more on something. There's something I did last year, and that was asking you to write the quantum numbers for different elements. Right? I will just try 1, 2 examples. You do the rest, and then we can proceed to something else. Look up, please. Let's get this man done, please. So, quantum numbers. In general, depending on your text you're using, some authors will call, of course, these are the basic ones. The first one is called the principal quantum number. And by the way, this one is not pronounced principal. It's pronounced principal. There is nothing like principal, quote me. The word principal is pronounced principal, not principal. So PAL and PLE are homophones. So you can do your research. Type this one, check it's pronounced principal, not principal. So the head of a secondary school is a principal. You want to see the principal, not the principal. So that's by the way. So when it comes to this man here, there are 4 types of quantum numbers. The principal quantum number, that's N. The azimuthal quantum number, that's L. The magnetic quantum number, that's M. And the spin quantum number, that's S. If you check in some text call this ML and this one as MS. Well, whichever thing they call it, we know what we mean. That's by the way. For this section, I want to show you 2 things. I'll kill, what do you call it? Kill 2 birds with 1 stone. Show you how to write the SPDF configuration in terms of another one there, and then how to get these ones for any elements. That's the task there. First things first, SPDF configuration. Do you know the order of the SPDF configuration? What's the order there? So the order is 1S, 1S, 2S, 2P, 3S, 3P, 4S, 3D. Alright, so it proceeds. Look at this, please. So let's see how to write elements in principal, azimuthal, magnetic, and spin quantum number, please. First is first. Take that, please. Let's use 1 for an instance. Take that, please. Take down. Write the SPDF configuration of fluorine. Write the SPDF configuration of fluorine given the values of each of the quantum numbers. Write the SPDF configuration of fluorine given the values of each of the quantum numbers. All right. So look up, please. I'll use for an example, and then we'll try a past question. I'll leave the past question to you, and then we'll see what we can get, please. Fluorine F. Please, atomic number, please. Atomic number is 9. So look up, please. Let's get 9 for this. For your SPDF, please. For S shell, what's the maximum number of electrons? 2. For P shell, maximum electrons 6. For D shell, maximum 10. For F, maximum. So I have 6, 2, 6, 4, 2, 6. So we have 2, 6, 10, 14. Look up, please. For fluorine, what's the configuration here? 1s squared, 2s squared, 2p5. That's all. All right. So look up, please. Look up, please. Let me show you get the quantum numbers using this. Am I still in the right frame? Check. Am I still in the right frame? Okay. Please get your next proceed, please. Take down, please. Now listen. Listen, please. First things first. Look up, please. First things first. For the principal azimuthal magnetic and spin, the easiest one to get is always the principal quantum number. How? To get your principal quantum number for this one here, n is equal to, you look at the last, if I look at this head here, the last shell or orbital per se is this one here. My last orbital is this one here. If I look at the number attached there, that's 2. Please, for n, look at the last orbital here. After you've done your SPDF configuration, the last one here, the coefficient here is 2. So n becomes 2. That's all, please. That's how I get principal. So do your configuration there. For the last shell there, look at the value of the coefficient attached to that. So n, the principal quantum number, is equal to 2. That's all. Next up, please take down. Note this, please. Note this, please. Number 1. For S, L is equal to 0. For P, L is equal to 1. I'll call this 2. 3. For D, L is equal to 2. Number 4. For F, L is equal to 3. Please note this thing, please. For S, L is 0. For P, L is 1. For D, L is 2. For F, L is 3. So if I've got this right, I've gotten my first quantum number. That's your principal quantum number. So the answer is 2 because in my last orbital, coefficient here is 2. That's all. Number 2, to get the next quantum number, the azimuthal, just look at this one here. In my last orbital, I think the last orbital is what plays the major role here. This last orbital, this one here. In my last orbital, if I look at this now, what I have there is a P. For a P, what's L there? So therefore, azimuthal L is equal to 1. Therefore, azimuthal L is equal to 1. Also note another set of thing. Note this. At L equal to 0, M is equal to 0. Number 2, at L equal to 1, M is equal to minus 1, 0, plus 1. Should I say plus? Okay, plus 1. Okay, fine. Use plus 1 there. Number 3, at L equal to 2, because L can be only 0, 1, 2, 3. At L equal to 2, M is equal to, look at please. The idea is simple. I'm starting from the negative of that number to what there? The positive. So when it was 1, I start from minus 1 to plus 1. For 2 becomes what there? Minus 2, minus 1, 0, 1, 2. That's it. Alright, number 4, at L equal to 3. What do I have there? M is equal to, so from minus 3 to plus 3, what do I get there? Minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Perhaps let me add plus here. So plus 1 plus 2. So please note this one, please. All right. Rephrasing this, please. So this one came out about 3 questions last year. That's why I'm stressing on this. They ask you to get the principal, azimuthal, magnetic, and spin. I've said some call this ML and MS is the same thing, right? All right, so I said your task is simple. Your first task is to get SPDF configuration. Everything boils down to the last orbital here, 2p5. For 2p5, your principal quantum number becomes 2 because the coefficient of the last orbital is 2. That's all. Next up, after principal, your L. For L, we said look at what you have here. Since this is P, we said for P, L is equal to 1. So I have L as 1. That's all. Next up, I want to get magnetic M. How do I get magnetic? We said for magnetic, the magnetic depends upon the azimuthal there. If I look at this now, we said at L equal to 1. In my case here, L is what there? 1. So since L is equal to 1, that means my M is equal to minus 1, 0, or plus 1. So how do I know which of them exactly it is? Now, here's what to do, please. I will come here, I will say minus 1, 0, and plus 1. Next up, I said everything boils down to this, please. How many electrons do you have here? 5. You try to do 5 configurations here. So it becomes, look up, just like when you're doing, if I were to do this in box, you know how it looks like, right? Up and down, is it not? Good. The same idea here. So I'm taking here 5. Now, first of all, fill them the first time. Up 1, up 2, up 3. Please, like this. You don't say 1, 2. That's wrong. First of all, fill the upper ones first. When you're done, come back and fill the lower ones. So for this, I'm having 1, 2, 3. Come down here. So I'm done filling the first one. 4, and then 5. Observe that 5 ends at 0. So since the last one ends at 0, therefore the magnetic quantum number is equal to 0. That's all. Just hang on, you get it. Just hang on. Just fill it up gradually. I'll do like 2-3 examples so to stick. First things first, 2p5. M is 2 because the coefficient here is 2. Okay, so what next? Look at what you have here. I have P. It is this one that will determine the value of L. Since P is, since I'm having P here, we said L will be 1. That's it. When L is 1, M is from minus 1 to plus 1. That means M will have 3 possible values, either minus 1 or 0 or plus 1. How do I know the exact value? I'll come back here, minus 1, 0, plus 1. Look at the number of electrons here, 5. So fill it up. So 1, 2, 3, come down, 4, 5. It got filled up or it ended at 0. So M is equal to 0. That's all. So I've gotten N, I've gotten L, I've gotten M. Let's get S. For S, what happens? Very simple. If the arrow is pointing downwards, it becomes a negative. Negative half. Please, spin is either negative half or positive half. That's all. Take down, please. If you're here, take down. Note that spin quantum number is either minus 1 over 2 or plus 1 over 2. Either minus 1 over 2 or plus 1 over 2. If the arrow points down, S is equal to minus 1 over 2. If the arrow points down, S is equal to minus 1 over 2. But if it points up, S is equal to plus 1 over 2. Please check the last arrow. Pointed, is it up or down? Points down. What happens there? S is equal to what there? So look up, please. This is how you present your work. So therefore, the quantum numbers include number one, the principal, two, so it becomes 2, comma, number two, the azimuthal L is 1, so I'm having 1, comma. Next up, the magnetic we got this as what? 0, so 0. Next up, spin, that becomes what there? All right, so this is how you do this, please. Just relax. I'll take a second example. Look at this. I'll take a second example. Yes, please. No, you're not listening. And Chief, why you ask about Lewis? You're not listening. I said the first one go up first. So it becomes 1, 2, 3, and then 4, and then 5. That's it. So fill up first. One it as well make you not to listen. No man, I'm kidding. Alright. Can I clean, please? Can I clean? Alright now, alright. Chief, you're in charge of that stuff. We'll make sure it's videoing properly. Take down, please. Find the quantum numbers for ion, Fe. Find the quantum numbers for ion, that's Fe. Given that the last shell is 3d to the power 6. Given that the last shell is 3d to the power 6. So I'm going to find 4 things here: principal, azimuthal, magnetic, and spin. Please, first things first, please. For this one here, what's the principal? N is equal to what there? 3. I'm done with this. Number 2, what's the azimuthal? L is equal to, for D, what's L? So it's equal to 2. I've gotten to that. Next up, let's get magnetic. So in this case, look up. Someone's asking why is D equal to 2? Look up. So listen. Why is L equal to 2? Because the shell here is D. And we said note for D, L is 2. That's it. So L becomes 2. Let's get M. Since L is equal to 2, what will be the range for M? M will be equal to minus 1, 0, plus 1, plus 2. So we know how to get the exact one. So I'll just come here as minus 2, minus 1, 0, plus 1, plus 2. My task is very simple. Try to fill this one up here with the number I have here. How many here? So fill it up with 6 electrons. The case is simple. Start with the upper ones first. So I'm having 1, 2, 3, 4, 5, finally 6. So I have 6 here. Alright. So therefore, since the last electron ends at minus 2, M is equal to what there? M is equal to minus 2. That's all. For S, for spin, Please, will it be plus half or minus half? Minus half. It will be equal to minus half. Why minus half? The last one is pointing down. So what will be the quantum numbers? 3, 2, minus 2. All right. Any questions, please? Let's try a past question now. Is anybody confused with this? Should we try one more example? Anybody confused? You said? Explain. Okay. Example 3. What are the quantum numbers for an element that ends with 4f to the power 5? What are the quantum numbers for an element that ends with 4f to the power 5? Power 5. I'll give you a password for you to try. First is first, please. Let's get this one done, please. First is first. For this man, please, what will be your principal quantum number? Very simple. This one here. That's 4. That's all. So I'm having 4. Number 2, azimuthal quantum number L. L is equal to get L, simply look at what I have here. Which letter is there? F. For F, this one here, what's L? 3. So since I'm having F here, L is equal to 3. I've gotten azimuthal. Next up, get magnetic. How? For magnetic, since L is equal to 3, what will be the range for M? M will be equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. That's M. Let's get the correct value of M. How do you do that? I will list this one out. Minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Next up, I will plot these configurations. This one says 5 valence electrons here, or perhaps 5 electrons here. Pick out these 5 electrons, plot them here. Don't forget, I'm going upwards first before I start going downwards. So 5, I'm having 1, 2, 3, 4, 5. So I have 5 at this point. So since the electrons ends at this one here, plus 1, it means that magnetic M is equal to plus 1. That's as simple as you can get. Finally, the spin quantum number S. We said S is equal to minus 1 over 2 or plus 1 over 2. How do you know the difference? Pointing downwards, negative. Going upwards, positive. Up or downward? So because we're there. So what's the configuration here? 4, 3, plus 1. So it's that simple. That simple, please. Please, this year, past question says, find the quantum numbers for potassium, please. Get the quantum numbers for potassium, please. You read to yourself. For potassium, get the 4 quantum numbers for potassium. What's your answer? All right, look up, please. Quick one, please. Let me not assume everybody knows. Let me show you this, please. Another thing they said last year, plenty, was how to write the SPDF configuration of a particular element in terms of another element. That's what they said last year. Let's start with hydrogen, please. Hydrogen H. What's the configuration there? 1s1. All right. Helium H2. What do I have? He. What do I have there? 1s2. Lithium Li. What do I have there? 1s2. 2s1. Beryllium. What do I have there? 1s2. 2s2. I want to get something. Boron. What do you have there? 1s2. 2p1. All right. So look at this, please. They said this stuff last year. They said, look at this, please. Here's the concept. I can write, they said I should write lithium. You should do the SPDF configuration of lithium in terms of helium. How do you do that? Look up, please. Look up. If I want to write the SPDF configuration of lithium in terms of helium, what I will do is simple. If I look at this here, this one here, 1s squared, describes the helium configuration. In other words, lithium becomes, this one is helium, you put it in a square bracket. So it becomes square bracket, helium, and then this one here, 2s1. So this is how you write it in terms of another one. Relax. Let's look at writing beryllium in terms of boron in terms of beryllium. What do you have there? Beryllium is equal to, observe that 1s squared, 2s squared describes this one here, describes beryllium. So it becomes what there? Beryllium into what there? So please note this stuff, please. We use them in general. So this is another concept you should know, that I can write the SPDF configuration of an element in terms of another element. This pattern, please.